So if I wanted to FOIL this first one, I could set this up. I'm going to do, all right, my first terms. So I'd have -4 times -4 to get a positive 16. -4 times a -5 to get a positive 20i. And then I'm going to have -4 times 5i would be a negative 20i. And then I'd end up with negative 25i squared. We can see that these are opposites, so those are going to combine to get 0. So I have 16 minus 25i squared. What is that I squared again? -1, okay? And we need to know that, okay? I squared is -1. So this becomes 16 minus 25 times a -1. So it becomes 16 plus 25. What's 16 plus 25? 41. Okay, so the key thing I want to take away from this one is that we had two complex numbers, but when we multiplied them, we don't end up with a complex number. In this one, we just ended up with the real part. There's no I left in it. We're going to focus more on this today. Sam?
If you square -1, would that make it?
No, you're not squaring -1. I squared is -1. So that is a relationship. I squared is -1. I is not a variable that we solve for. I is called the imaginary unit. It's just I, okay? So, but if I square I end up with -1. Okay, what was the other relationship? So what is I then? Square roots of -1, okay? Those two, you need to make sure you are solid on those two. I squared is 1. I is going to be square roots of -1. Do whatever you need to do to memorize those. You need to know those. Working with imaginary numbers, if you don't know those, you're going to make mistakes. All right? And then the second line, I just have a couple division pieces. So 5 divided by 5 is what? 1. And then x divided by x is what? 1. So what do you think 2 plus 3i divided by 2 plus 3i is? 1. Okay? This relationship we are going to focus on today. If I have an imaginary number and it is the same top and bottom, I'm simply going to treat that as 1. So we need to know this relationship or be comfortable with this relationship today as we go through this lesson. Okay. First thing we're going to talk about what are called complex conjugates. Complex conjugates are number pairs of the form a plus bi and a minus bi. All right, so we can think of that imaginary part, the bi part, are opposites. Okay, because it goes a plus bi, a minus bi. And if you look back at our warm-up, we had that. Okay, we had on our warm-up -4 plus 5i, -4 minus 5i. All right, the imaginary parts were opposite signs. Okay, and this is some terminology you need to know, because you're going to hear me start saying, well, what is the complex conjugate? We have to use the complex conjugate. Let's look at the complex conjugate. You need to know when you hear me say that simply we're just looking at the opposite sign on the imaginary part. All right, the product of complex conjugates is a real number. And that's exactly what we did in that first warm-up. The product, meaning multiplication, if we multiply complex conjugates together, we end up with just a real number. That first warm-up problem, we ended up with 41 because those two were complex conjugates. They had opposite imaginary parts. When I say opposite, opposite sign again. Opposite imaginary parts. So whenever you multiply complex conjugates together, you will always end up with just a real number. There will not be any imaginary part to it. Okay, that was our warm-up one. And last thing, complex conjugates are used to simplify quotients. Quotients just mean fractions, doing division of complex numbers. So now today we're going to spend all our lesson on dividing complex numbers. Adding, subtracting, multiplying were pretty straightforward. There's a little more work to dividing complex numbers, but we're going to use this idea of complex conjugates to help us and be able to work through the problems. Okay, so let's actually do one. If I had these two complex numbers, 9 plus 12i, and then a pure imaginary number in the denominator, which is just 3i. There's no real part to it. One thing I do want to notice, though, there's no real part to it, but it is a positive 3i. So if you want to put a plus sign there, you can, just to remind yourself that it's positive, okay? Or to simply be able to look at it and know that it is positive. Okay, what we want to multiply by is always going to be the complex conjugate of the denominator. Okay, so we want to multiply by the complex conjugates of the denominator every single time. Okay, we're only looking at the denominator. So what is the complex conjugate of 3i? Eli? Negative 3i. All right, we're just looking at the opposite sign. And we're going to multiply by negative 3i divided by negative 3i. Because again, what is negative 3i divided by negative 3i? 1. So all we've done to our problem is multiply by 1. But within that 1, there's some stuff that we need. Okay? We are introducing this complex conjugate because now when I multiply, I'm guaranteed to get a real answer in the denominator. Okay? So all we have to do is simply multiply through. 9 plus 12i, treat that as one entire complex number. If you need to put parentheses around it to remind yourself, do that. But this is one complex number. So 9 plus 3i times a negative 3i. We're only working across the numerator right now. Okay? With multiplication, we can multiply a real number and a complex number together. I'm sorry, a real number and an imaginary number together. So this is going to be distributed here and here. Negative 3 times 9 would be a negative 27i. Negative 3 times 12 is going to be a negative 36i squared. In my denominator, positive 3i times a negative 3i will give me a negative 9i squared. Now let's do some simplifying here. Well, I know this I squared and this I squared are really negative 1. And so I can rewrite this as negative 27i. Negative 36 times a negative 1 would be a positive 36. Negative 9 times negative 1 would make that a positive 9. Okay, so I'm just going to rewrite this, and I'm going to write it in proper complex form, complex numbers. So this would be 36 minus 27i, all divided by 9. And now this is something we ran into on the last test that we took. I have subtraction going on in the numerator, going back to elementary math. If I'm subtracting fractions, I have to have a common denominator. They're writing it as 9 as my common denominator. I'm going to break this up. I'm going to say, well, this is really 36 divided by 9 minus 27i divided by 9. Okay, we're going to group those two together. The 9 is not only applied to one term in my numerator, it goes to both. What is 36 divided by 9? 4. What is negative 27 divided by 9? Negative 3i. So here's our final answer. Okay, so the quotient of 9 plus 12i divided by 3i ends up being 4 minus 3i. Eli. No, so don't think of I as like a variable. I is this representing the imaginary units. Okay, so no, I wouldn't think of it that way. All right, but the big thing here was understanding that we have to multiply by the complex conjugate of the denominator. Box that in, star that, whatever you need to do in your notes. That is the most important step when dividing complex numbers. Okay, you cannot forget that. And students forget it every year when we take our tests, which is going to be this Thursday. They end up multiplying by a positive 3i over 3i, or they multiply by 9 minus 12i all over 9 minus 12i. Can't do that. Complex conjugate of the denominator. And do not get confused if there's not a real part to it. It was a positive 3i, so I have to multiply negative 3i over negative 3i. And I can do that because really all I'm multiplying is by 1, but it's getting me into a form that I can work with. Okay, this one, 2 plus 3i divided by 1 minus 4i. What am I going to multiply by? Eva. 1 plus 4i over 1 plus 4i. Okay, that is the complex conjugate of the denominator. And now this one, remember, these are all complex numbers on their own, and we are multiplying, and so we're essentially going to be foiling to work through. One. No, it's only the sign in between. Only the sign in between them that changes. It's the sign on the imaginary part. Okay? Go ahead, you do this one. Take a second here, see what you come. Okay, let's pick up doing this one, even if you're not finished yet. So, if I'm only working in the numerator, I have 2 that I need to, 2 complex numbers that I need to multiply together. So I'm going to use my FOIL. And so this would be 2 times 1, which is 2. 2 times positive 4i, which would be 8i. 3 times 1, or 3i times 1, which would just be 3i. 3i times 4i to be a 12i squared. Denominator becomes 1 times 1, which is 1, plus 4i minus 4i, and then minus 16i squared. All right, I can see these go to 0, so I don't have to worry about that. Now in my numerator, I'll have 2 plus 11i, 12 times I squared. I squared again is negative 1, so it's 12 times negative 1, so this becomes minus 12. In my denominator, I have 1 plus negative 16 times a negative 1, and so this would be plus 16. So finishing up down here, I can still simplify my numerator. 2 minus 12 would be a negative 10 plus 11i all over 17. But again, I do not want you to stop here. I want it in the form a plus bi. So I only want a coefficient on the imaginary part and a real part. So again, I can break these up. They each have a common denominator of 17. So it becomes negative 10 divided by 17 plus 11 divided by 17i. So I went all the way down into that. And if it's one that you can simplify, like if you got 10 over 2 or something like that, we could simplify that to be 5. So look at your fractions, see if you can simplify those. These ones we cannot. Negative 10 over 17 stays as that, and 11 over 17 stays as 11 over 17. So separate it as a real part and an imaginary part. If you stop at the step prior where it's negative 10 plus 11i all in the numerator divided by 17, I'm going to take points away. Okay, I want it in the a plus bi form. Questions on this one? Okay, again, most important step, multiplying by that complex conjugate, 1 plus 4i. All right, so let's put this to work. If I wanted to find all solutions to this, and spoiler alert, we're going to have some imaginary solutions. Okay, so all this stuff with this imaginary unit I lets us do negative square roots, or square root of a negative number. Now we can look at all solutions. They don't have to be real solutions. Okay, prior to this section, we would stop when we got a square root of a negative number. Well, now we have the tools to go ahead and solve when we have a square root of a negative number. So how do I attack this? How could I find all solutions? Landon, what would you do? Okay, so is this one factorable? Okay, so it multiplies to get 10, and then it adds up to be a negative 3. Are there two numbers that we can multiply to get 10 that add up to be a negative 3? Eva. Eli. Okay, that would give us a negative 10. Okay, so this one is not factorable. Okay, so we can't use factoring. Eva, what would you do now? Okay, quadratic formula is powerful because we can use it on any of them. Completing the square, we could do completing the square, but that 2 on the x squared would mean we have to divide every single term by 2, and then we're getting these fractions, and it's going to get kind of messy. So you could use completing the square, but let's just use quadratic formula. So quadratic formula again, negative b plus or minus square root b squared minus 4ac all over 2a. What is my a, my b, and my c in this quadratic that they give me? No, what's a? 2, what's b? Negative 3, what's c? 5. Okay, so negative b, or you can think of it as opposite of b, so this is going to become positive 3 plus or minus square root of negative 3 squared minus 4 times my a, which is 2, my c is 5, all divided by 2 times 2. So I have 3 plus or minus. Let's figure out what this discriminant is. So negative 3 squared would be 9 minus 4 times 2 times 5. 4 times 2 is 8. 8 times 5 is 40. So it's 9 minus 40. What's 9 minus 40? It's what? Negative 31. All right, so under my radical here, I have a negative 31. And it's going to be all divided by 4. So up until this section, we would stop because we can't do square root of negative 31. Well, now we can work with square root of negative 31. Let's work with our imaginary units. So square root of negative 31, again, I can write that as negative 1 times 31. So I can break this apart and say square root of negative 1 times square root of 31. What is the square root of negative 1? I. So this is I root 31. So I can continue on with my problem here. So now I have 3 plus or minus I root 31 all divided by 4. Okay. And this is one, square root of 31 is not one that I can simplify. There's not a perfect square that is a factor to it. So I can leave this one just like this, okay? If you took it a step further and said 3/4 plus or minus, we'll just say I root 31 over 4. You could do it like that too. Okay, that is separating the real and the imaginary parts. But if you got to this step with this one, I would be fine. Okay, so this now completes to 3 plus or minus I root 31 divided by 4. And again, x equals that. So what we will say now on this one is we would say that there are no real solutions. All right, square root of 31 stopped us, so there's no real number that we could do, but there are 2 imaginary solutions. The 2 imaginary solutions are 3 plus I root 31 over 4 and 3 minus I root 31 over 4. So there's 2 imaginary solutions, but there are 0 real solutions. And again, by saying 0 real solutions, all this really is, we still have a quadratic that we could graph, but it's simply going to be above the x-axis. It's never going to touch the x-axis. So there's no real solution. There's nowhere where it's crossing the x-axis, but there are 2 imaginary solutions to it. So 0 real, 2 imaginary. If I asked you for the number of solutions on this one, that's what I'd look for. I want you to specify 0 real, 2 imaginary. Landon.
Say we had negative 16 to 31.
Okay.
Would it then be 4?
Yep. Yep. So if you did get to a perfect square, if you got square root of negative 16, Landon was saying, then we could do I square root of 16, so it'd become 4I, but it would still be plus minus 4I. Yep, and then we could keep going, and then that'd be an easy one we could break apart. But the big thing I want to get across here is this new idea where now we can say there are 2 imaginary solutions, and they are 3 plus I root 31 over 4, and then 3 minus I root 31 over 4. Eva. Correct. Yep. Okay, so for your assignments, just a textbook assign on this one. 253, 27 through 31, 39 through 43, 48, 53, 54.